Welcome back, ladies and gentlemen. In this video, we're going to look at circuits that have something in series and something in parallel. And you call that a compound circuit. It's a combination. You might call it a combination circuit. It's the same kind of idea. Here in the first example, we have R1, and it looks like R1, if you thought of R2 and R3 as one thing, then if this were sort of just one thing here, then R1 would be in series with that one thing. And here, in this example, then R1, if you thought of R2 and R3 as one thing here, then R2 and R1 would be parallel to this one thing. So how do you deal with this? Well, here's one of the ways that I like to think of this. Which do you tackle first? Can you deal with combining R1 and R2 and ignore R3 at first? Well, the only way I can really see that R1 is in series with R2 is if I hide R3, if I get rid of it. Because with R3 there, it's kind of screwing things up in terms of how these two are related. Same thing going on here. Well, the only way I can see that R1 and R2 here are in parallel is if I hide R3. Because R3 is kind of messing with that relationship a little bit, because R1 isn't just in parallel with R2 because of this. R1 is not here just in series with R2 because of this. But check this out. What if I cover R1? Then are R2 and R3 still in parallel? Well, yes, they are. And if I bring R1 back, are R2 and R3 still shown easily seen to be parallel? Yes, they are. So here's the deal. That's the tricky part, and it's just about visualizing. Well, what's the sort of closest relationship you can find? And it might be two resistors. It might be more than two, but I can deal with these in parallel, and then deal with these here and this whole thing in series. Here I would deal with these in series first, and then deal with R1 and this whole thing in parallel. And so what do you do first? That's the tricky part. Now, I'm not going to do both of these. It would just take too long. I'm going to show you one of these circuits. Let's go with this guy. We're going to solve a bunch of stuff for a circuit that looks just like that. So here we go. Let me redraw it here so we have it handy. We have a voltage source. That. And there's this other thing here. Okay. And we have, let's say we give this a 12 volt source, and we call R1 and R2 and R3. Well, you know what? Let's just make them all 5 ohms. Easy number to deal with. Okay. So here's what we're going to calculate from this circuit. Here's our job. Here's our task. We're going to find the equivalent resistance of the whole circuit. We're going to find the current coming out of the source. And another way of saying this is the total current. So, parentheses there. We're going to find all voltage drops in those resistors. We're also going to look at the individual currents through each resistor. And lastly, we're gonna bring back some older concepts and look at how much energy. Come on, paper, don't move. Is used. We might also use the word dissipated. 2 S's. Used or dissipated in each resistor in, let's say in 1 minute. If we run that for 1 minute. So we're going to find all of these things. And it'll take us a little bit of work. It's not bad. It's not bad, especially once you see the process. So remember, what I need to do is first realize what can I combine first? What's the thing I have to deal with first? If I cover R1, R2, and R3 are definitely in parallel, and there's no doubt. Bring back R1, and it doesn't mess up this parallel nature. This is the first thing I'm going to look at right there. And it's just something you have to see. It's a little bit of just you have to recognize that. Now, first step, what I'm going to try to do is just outline the steps. I'm going to find this. I'm going to find REQ of 2 and 3. So I'm going to find R2, 3, which is those two combined. And what I know about 2 and 3 is they're in parallel. Just a little note to myself that that's what I'm doing. Okay. When resistors are in parallel, the equivalent sort of equation here is the whole fraction within fraction. I have two of them, so I go 1 over 5 ohms plus 1 over 5 ohms, and that gets me 1 over 2/5, and that gets me 5 halves, or 5 halves is 2.5 ohms. So I'm going to rewrite it so it's perfectly clear. Okay, now that's not an answer I need all by itself, but it's a step in the right direction. And so I'm going to do a redraw. I'm going to go green on my redraw of the circuit. It's going to be like this. I've got those two combined now into R23. So I have a voltage source, and I have R1, and now here I've got this guy, and I will call this R23. And the reason for redrawing is it now lets me see that, well, I've got R1 in series with this thing, and this thing is equal to those two, right? Now, I've got R1, which was 5 ohms, and I've got R23, which was 2.5 ohms. Okay, I'm running out of space. Here we go. The next step is essentially going to be the final step for overall resistance. And when you're getting the final step, that's your equivalent resistance. I reserve this for the equivalent resistance of the whole circuit. And really that's what you want. And what I have to recognize is now at this stage, I have a series relationship here, one after the other. So that's what I will use. And so this is going to be equal to R1 plus R23, which is 5 ohms plus 2.5 ohms, which is 7.5 ohms. And I'm just going to quickly write it. 7.5 ohms. That is an answer I need. So I put a box around it so I can find it easily later on. Very cool. And so really, if I want help understanding what's going on, well, at this point, I just have a voltage source, and I just have one resistor, and it's REQ. And so the overall resistance of this circuit, this guy here, the overall effect is just 7.5 ohms. That's pretty cool. Now what do I do with that? Well, the next task I have to do, where'd the list go, right? So I've done this, check that off. I need the total current, right, or current through the source. Well, that's easy. What I'm going to do is I'm going to use Ohm's law. And So this is a current through the source. Ohm's law says that current is equal to voltage divided by resistance. What voltage do I use? Well, the voltage I use is very straightforward. It's going to be the voltage of the source. And the resistance I use is going to be the equivalent resistance. The voltage of the source was 12 volts. The equivalent resistance was 7.5 ohms. And 12 divided by 7.5, 1.6 amps. Rewrite that real quick. That was easy, right? That's an answer I need. That is this guy. Check that off the list. Cool. It's really going to come together pretty quick for you once you get all these steps. Next on the list, I have to find the the individual voltage drops of each resistor. How much does this resistor drop the voltage? How much does that one and that one? So here's what I have to do. I'm going to go with some new paper here just for the space. Okay. Find V1, V2, and V3. Well, again, I'm going to use Ohm's law. Watch how this works. Ohm's law applies to the whole circuit, certainly, but also applies to each individual circuit. So V1 is equal to I1 times R1. But the thing about this is, well, if you look at the circuit, where'd the circuit go? I have to look at the picture of the circuit. How much current's coming out of the voltage source, and how much of it goes through R1? Well, all of it goes through R1. So that's just something I have to see. R1 is basically in series with the voltage source. All the current coming out goes into and through R1. So I can also say that the current through 1 is equal to the current from the source. And so I'm going to rewrite that to show that. And I know how much current that is, and I know the resistance of R1. So watch this. Voltage drop of 1 is equal now to the current through the source times R1, and that is 1.6 amps. And R1 is 5 ohms. And I get 8 volts. 1 equals 8 volts. Rewrite so it's clear. Box around the answer. And I'm on my way. Now I'm going to find, I can't go right to finding voltage drop of 2 and 3 because I have to acknowledge something first. Instead of voltage of 2 or voltage of 3, I've got them combined right here. And I've got R23. So there is a voltage drop across R23. Even though it's sort of an equivalency, I can talk about the voltage drop of 2,3. Well, here's the deal. It is equal to the current through 2,3 times the resistance of 2,3. Cool. Do I know the current through 2,3? When I look at this picture, well, the current through this part will be the same as the current through R1. And I know what that was, so that's cool. And I also know the resistance here. So I know current and resistance, I can find the voltage drop of 2,3. So I got 1.6 amps. And I have equivalent resistance, that was 2.5 ohms. So 1.6 times 2.5, and I get 4 volts. So 4 volts. Now that's not an answer I'm looking for, so I'm not going to put a box around that. However, what I know about parallel circuits, so for parallel, because now I need to break up this R23 into 2 and 3, so those are in parallel with each other. So for those things, for parallel resistors, what do I know about voltages? I know that, well, the voltage of 2, 3 combined is equal to the voltage of 2, and it's equal to the voltage of 3. That's real slick. So each of those is equal to that, and that's 4 volts, so each of those is 4 volts. Therefore, V2 is 4 volts. That's an answer I want in a box, and V3 is also 4 volts. Put a box around that guy. I have the voltage drop of all 3 resistors. Now let me mention this real quick for you. So check this out. There's a voltage drop here from R1, and that voltage drop was 8 volts from R1. So now R2, 3 combined has to take care of the remaining 4 volts. And so if I imagine covering this up, and 8 volts has already been dropped, we have 4 volts left over, so to speak. And now R2 is going to look straight back and see that 4 volts, and R3 is going to look straight back and see the same 4 volts. This is an equipotential along the wire here and along the wire here. So it's a 4 volt difference there and a 4 volt difference there. Okay. Now, what have I accomplished? I have found the voltage drop across each resistor. Check that off the list. Now I want to find the individual current flowing through each resistor. Okay. Individual current. That is page 5 now. I'm now going to find individual currents. And so this is going to be I1, I2, and I3. Individual currents through each resistor. So how do I do this? Well, I've already figured out that I1 is equal to IS, right? The current through 1 is the same as the current from the source. Just there's no option. All that current has to flow through R1. And so from this right away, I have the first answer, 1.6 amps. So from that, I say that 1 is 1.6 amps. Okay. What about I2 and I3? So for these guys, I'm going to use Ohm's law again. A current is equal to a voltage divided by a resistance. Do I know the voltage drop of 2? Yes, I do. Do I know the resistance of 2? Yes, I do. So I've got these numbers. Voltage drop of 2 is 4 volts. Resistance was 5 ohms. And so 4 divided by 5, you get 0.8 amps. So I2, current through 2, was 0.8 amps. Box. Definitely one I'm looking for. And finally, I3. Voltage 3 divided by R3. You have 4 volts. And the resistance of R3 was 5 ohms again. And so 0.8 amps. So I3, 0.8 amps. Okay. Cool. Now, it looks like I have finished finding individual currents. That was pretty fast. I can check this off the list. I just have one more step to go through. I have to find the energy dissipated in each resistor in 1 minute. All right. So in order to do this, let's see. I'm tired of blue. Let's go to the green. Okay. In order to look at the energy dissipated in 1 minute, that's what I'm going to find. Energy is a capital E, and I'll just write the word used because it's shorter. Used in each resistor in 1 minute. What am I going to use? I'm going to use the relationship from power. Power is equal to, just in very general terms, energy divided by time. And that's interesting. That's cool because I have a time. I want an energy. Well, what about the power side? I'm also going to use the fact that in an electric circuit, the power is equal to the current times the voltage. Oh, and so if in here, I substitute I times V, current times voltage, and instead of the P. And then I will multiply both sides by T. So I have E equals T, there. And multiply both sides by T, I have energy on one side of the equal sign, and I have current times voltage times time on the other side. Do I know the current flowing in the circuit? Yes, I do. Do I know the voltage supplied to the circuit? Yes, I do. And I know the time. I'm golden here. So the energy dissipated, oops, but that's the total energy, isn't it? Okay. So I can apply this, though, to resistor number 1. Do I know the current through the resistor number 1? Yes, I do. How about the voltage drop of resistor 1? Yes, I do. And the time, I'm golden. I'm fine. So the current through R1 is 1.6 amps. The voltage drop of R1 was 8 volts. And the time, well, I've told 1 minute, but I need the time to be in seconds, 60 seconds. And so when I do that math, I end up getting 768 joules. In 1 minute, R1 will use up or dissipate 768 joules of energy. That's an answer I was looking for. Box. Okay, I'll do the same thing for the other 2 resistors. I'm going to see if I can squeeze it all in one paper here. Divided the space so I have organization. So E2, I'm going to use the exact same equation. So the current through 2 was 0.8 amps. And the voltage drop of 2 was 4 volts. And the time is still 60 seconds. So when I do that, 192 joules, that's E2. It's starting to get easy. I'm starting to see all this. Energy dissipated by resistor 3, same equation. The current through 3 was 0.8 amps. The voltage drop of 3, I need a 4 volts. And the time is still 60 seconds. 192 joules. Wow, okay, we got a lot of answers, so check this out. I'm going to real quick recap of what we have found. So the original page here was, there we go. So we started by looking at 2 examples, trying to figure out, well, how do I approach this? This is the hardest stage, really. Trying to see, well, what do I deal with first? Do I deal with these 2 first, or 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 these 2 first? And you got to think small, think locally. And so I had to do the parallel first here, or if this was my circuit, I'd have to do the series first here. Okay, then here's our example, and I have to find equivalent of R23. I have to use that to find the overall equivalent resistance, and that's what I've got here. And that represents the resistance of the whole circuit in one deal right there. Then I had to find the total current. I used Ohm's law and got the current coming out of the source, which is also called the total current in the circuit. Then I found the individual voltage drops using Ohm's law. Ohm's law is V equals IR. And I found the voltage drop of 1, voltage drop of 2, and 3. There was a little trick here I had to do because these are parallel, 2 and 3 are parallel with each other. Then I found the individual currents through each one. Current through R1 is, look at that, it's larger. In fact, it's equal to the sum of those 2. That's kind of curious, but that makes sense because you know that the in a parallel, oh sorry, these 2 are parallel to each other, but this and this are in series. So what I would have to do is add these 2 together, and you get, well, it works out, you get that. I don't want to take this video any longer than it is. You find the individual currents, and finally we had to look at the energy used in each of those individual resistors. So I had to look at the power relationship generally, but also the power relationship for circuits specifically, and I did a quick substitution these guys into for P, and I got my energy, and I knew all those values. I got the answers measured in joules. Awesome. That's how you analyze a circuit, ladies and gentlemen. Thanks for watching. I'll catch you next time.